Hello students, this is my third lecture on real analysis. In the previous lecture, I have discussed D'Alembert ratio test. In this lecture, I will discuss Cauchy's nth root test. The statement is, let summation un be an infinite series of positive terms and let limit n tending to infinity un power 1 by n is equal to L. Then the series summation un is first convergent if L is less than 1, second divergent if L is greater than 1, and third test fails if L is equal to 1. So let us prove this theorem. Since un power 1 by n tends to L as n tends to infinity, therefore from the definition of limit, it follows that there exists a positive integer m such that un power 1 by n lies between L minus epsilon and L plus epsilon. That is, L minus epsilon is less than un power 1 by n is less than L plus epsilon for all n greater equal to m, and epsilon is greater than 0 and a very small quantity. Take it as equation 1. So consider case 1. Let L less than 1. Then we can choose epsilon such that L plus epsilon is also less than 1. Since epsilon is a very small positive quantity, so L plus epsilon is less than 1. From second inequality of equation 1, we have un power 1 by n is less than L plus epsilon. From here we can write that un is less than L plus epsilon whole power n. So now summation L plus epsilon power n is a convergent series as it is a geometric series with common ratio L plus epsilon, and L plus epsilon is less than 1. So L plus epsilon power n is convergent and hence summation un is also convergent. Now case 2, let L is greater than 1. Then again we can choose a quantity epsilon such that L minus epsilon is also greater than 1. From the first inequality of equation 1, we have L minus epsilon is less than un power 1 by n. This implies L minus epsilon power n is less than un, or we can write un is greater than L minus epsilon power n. Now summation L minus epsilon power n is a divergent series as it is a geometric series with common ratio L minus epsilon greater than 1. Hence summation un is also divergent. Case 3, if L is equal to 1, the above test fails, so the series may be convergent or divergent depending upon the nature of the series. Let us consider two infinite series, summation 1 by n square and summation 1 by n, in which one is convergent and other is divergent. If un is 1 by n square, then limit n tending to infinity un power n by 1 by n is equal to limit n tending to infinity 1 by n square power 1 by n, which is equal to 1. And summation 1 by n square is a convergent series by p series, as p is equal to 2 here, which is greater than 1. Now if un is equal to 1 by n, then also limit n tending to infinity un power 1 by n is equal to 1, but the series summation 1 by n is divergent by p series as p is equal to 1. So we can see that in the first case it is a convergent series when n is equal to 1, but in the second case it is divergent series and L is equal to 1. So if L is equal to 1, then the test fails. Take an example. Test the convergence of the series n to the power n square divided by n plus 1 to the power n square. So here un is equal to n to the power n square by n plus 1 to the power n square. This can be written as n by n plus 1 to the power n square. So here un power 1 by n is equal to n by n plus 1 to the power n. So if we find limit n tending to infinity un power 1 by n, we will get limit n tending to infinity n by n plus 1 power n. This further can be written as by taking n common from the denominator, n to the power n and n to the power n from numerator and denominator will be cancelled out, and we are left with limit n tending to infinity 1 by 1 plus 1 by n to the power n, which is equal to 1 by e, and this quantity is less than 1. Hence, by Cauchy's nth root test, summation un is convergent. Solve some more examples using Cauchy's nth root test for practice, and in my next lecture I will discuss Rabi's test.